Hello students, welcome back to this new session. In this session I am starting with module 2. In module 2, as you see, there are basically two parts. One is based on conformal transformations. There will be discussing certain transformations known as w is equal to e to power z, w is equal to z plus 1 by z, and w is equal to z square. These specific transformations we need to discuss in detail, and later on we have to discuss about bilinear transformations as well, and we have to solve certain problems based on these. Okay, this is about the first part of this module. In second part we'll be doing completely we'll be working with the line integral of a complex function and certain important theorems based on that. Okay, namely the Cauchy's theorem and the Cauchy's integral formula. We'll be deriving the Cauchy's theorem, we'll be proving Cauchy's theorem, and we'll be deriving the Cauchy's integral formula, and we also solve certain problems in this entire module. So now, to begin with, I'm not going to start with this theoretical type of discussion which we have to do in this module, that is the first part. What we will do is, we'll start with the second part first. We'll understand what all types of problems, how to work with the problems here in this entire part of the second module. Okay, the second part of the second module. First we'll do with this, then we'll move back and discuss all those in detail. Okay, there is a bit of theory and a bit of discussion that we have to do with these transformations in detail, and later on we have to work certain problems based on bilinear transformations. Okay, that we will do in the later sessions of this module. In the beginning, we'll begin with the line integral of a complex function. Okay, first let us understand what do you mean by the line integral of a complex function, and let us derive all the important theorems based on that, and then work with the problems. That is the second part we'll be concluding first, then we'll go back to the first part of this module. Okay, let's continue with this. Let us understand what is the line integral of a complex function. Okay, consider a continuous function f of z defined for all z is equal to x plus iy on the curve C. Okay, which is joining the points, or which is extending from P to Q. Okay, which is extending from P to Q as shown in the figure. I'll just draw a figure for you. Say this is xy plane. 1 minute. Say this is x, this is y axis, x-axis, y-axis, and the origin. You have the curve C, okay, which is extending from P to Q. For each and every point on this curve C, the function f of z is defined and it is continuous. Okay, now how do you take a line integral of this? What we do is, we divide this curve C into small parts, say n parts, right from P. Say I am going to call the point at P as z0. Right from here, say this is z1. So the point responding to z1, I will call it as P of z1. Say this is z2. I'll call this as P of z2, and so on. At the end, you may have zn, and the point corresponding to z1, I can call it as P of zn is equal to q. Okay, for each and every point I have all this. Okay, I am dividing this curve into n equal parts. Okay, now what I will do is, I'll consider a point alpha k. I'll consider a point alpha k sitting in this, an arbitrary point sitting in this part of the curve, or arc of the curve, I should say. Part of the curve is usually known as arc, you know, right? Yes. So sitting in this arc, an arbitrary arc, say that alpha k is belonging to the arc between, okay, is a point on the arc connecting pk and pk minus 1. Okay, okay, and let delta zk be the arc length, of that arc where alpha k is sitting on that, I mean where alpha k is the point. Okay, now what I will do is I'll do it for each and every point. I mean to say I'll do it for each and every part of the curve C. Small parts do I have? N equal parts I have, right? For each and every part of that curve C, I'll consider one arbitrary point alpha k belonging to that interval or belonging to the part or the arc of the curve, and then I'll also consider the length of that arc where that point has been considered. Okay, then what I will do is I'll find what is alpha f of alpha k, and I'll multiply it with the distance of the arc length of that arc we are considering. Okay, I'll do it for each and every part of the curve, okay, or arc of the curve. Okay, so and I'll consider the summation of it. I'll take the summation, I'll add all of them, k going from, because it stands for k going from 1 to n. So for each and every part of this curve or arc, I will consider one point, we'll find f of alpha k, and then we multiply it with the arc length. Okay, for each and every part of that arc, every part of that curve, we are going to do it. Okay, we have different arc lengths, we will have all that. Okay, and after that what I will do is I'll get a sum of all those points. Okay, I'll get different f of alpha k's into delta k's, set of all that, n set of all that, because I have divided that into n equal parts. Okay, now what I will do, I'll add all of them simply. Now this is not, I'm not going to stop here. I'll consider the limit as n tending to infinity. Now if I do the partition to such an extent that n is tending to infinity, means you can imagine the partition level. It is so small that n is tending to infinity. Okay, if I take a limit to this summation as n tending to infinity, this becomes the line integral, and we write mathematically it as integration over the curve C f of z dz. This is the line integral. Okay, this is the line integral. Actually, mathematically, this is the exact definition of line integral. Okay, this is, we write complete definition, we write it in one single way, that is integration along the curve C f of z dz. Now this curve C is moving from P to Q. The basic meaning of it is actually this. Okay, we take the partitions and we define each and every point. At each and every point we'll find the value of f of alpha k, that is alpha k. Alpha k is a point on that curve, on that arc, is it not? And we multiply it with the distance or the arc length, and then take the summation for each and everything. Okay, now if I do it, extend it for n tending to infinity, this becomes integration of the curve C f of z dz. Okay, this is the basic definition for the line integral. Okay, hope you have understood it. Now let us move on to some important theorems based on this line integral. Okay, now before going to the line integral theorems, I want you all to understand what are the properties of line integrals. First we'll discuss them and then move on to the theorems on line integrals. Okay, here we go. Now let us continue with the properties of complex line integral. Okay, now see, for any curve C, okay, any curve C, suppose it is connecting the point from P to Q. Okay, then minus C will connect the point from Q to P, is it not? Right? So therefore, integration over the curve minus C f of z dz will be equal to minus under integral sign C f of z dz. So I hope the point is clear. When C is connecting the points from P to Q, then minus C will obviously the opposite of it, that it will connect the point from Q to P, right? So if we are going from there, it will be in the negative this. So it will be integration from minus C, okay, integration over the curve minus C, like this. If this is P to Q, this direction is C for us. Minus C will be this direction from Q to P. Okay, then second one, and therefore integration over the curve minus c f of z dz will be minus of under integral sign f of z dz. Okay, it will exactly the negative of it. Then if c is split into number of parts, say C1, C2, C3, so on up till Cn, then integration of the curve C f of z dz will be integration over C1 f of z dz plus integration over C2 f of z dz plus so on plus integration over Cn f of z dz. Okay, I hope this is clear to you. Okay, third point of it, if C1, okay, I'll not take C1 and C2, I'll take say A and B are any constants, then integration of the curve C, A into f1 of z dz, I'll not take directly dz here, plus b into f2 of z or plus or minus f2 of z dz, will always be equal to a under integral sign c f1 of z dz plus or minus b under integral sign c f2 of z dz. Okay, I hope it is seen there. Yes, this way. If A and B are any two constants, now first second part let me explain it. If C is made up of so many parts of C1, C2, C3 so on up till Cn, then integration over the curve Cf of z dz will always be equal to the integration along those small parts, addition of all the integration of all those small parts. Like if you can consider it here only, see, say this is the curve C and it is made up of say from here till here, from this point to this point say it is C1, from this point to say it is C2, so on up till Cn you are having. Okay, then in addition of all those, integration along all these C1, C2, C3 you have to do and add all of them, you will get the integration along that curve C. Okay, and if A and B are any two constants, then this integral over the curve C, A into f1 of z and f1 of z and f2 of z are any two continuous functions of the complex variable z, then this linear combination of f1 and f2 can also be written like this. Okay, plus or minus this. Okay, I hope this point is clear to all of you. Let us continue with some more important theorems in my coming sessions. Till then, thank you.